So they have really started using it and getting very accurate numbers. When it comes to accurate numbers, we should know so far what kind of accurate number they have got. Because chemistry people, as Professor Paul was mentioning, already have good methods where they know how to take care of quantum correlations and get very accurate results. In that regards, Neetik is a postdoctoral fellow here with Dr. Amran Kusum Roy. They have a very sophisticated density functional theory-based methods, ab initio methods, which have been developed here, so which gives you very good results. And now, particularly, Neetik looks at atoms and molecules in a confined environment. For example, if you put atoms free space like hydrogen, it has certain property. But in many physical conditions, you find them confined in certain systems. Like, for example, if you would like to use them as a quantum computer, you would like to confine them. The properties will change. So listen to Neetik very carefully, because the kind of things he's going to describe is going to be of practical use. So Neetik, the stage is yours.
Okay, thank you very much, Professor Panigrahi, and I am also grateful to you for giving me this opportunity to share some of my work. But in this tutorial, I'd like to discuss about the initial confined system that we were taught during our undergraduate days, that particle in box, and how the change in boundary condition impact on its wave function. Then later we will follow how their energy is calculated, and after that we will study the uncertainty principle. So before start talking about confined system, let us begin with a free system. Know that systems are.
Sir, can you turn off the annotations option, because then there are people who actually use it to draw on the screen. So can you please turn that off?
Hello?
Yeah, sir, can you turn off the annotation option, sir, this marker option, because then students use it to actually draw on the screen while you are presenting.
Once again, I'm asking you.
Go to view options.
Sir, you have to switch to Zoom option.
Switch to Zoom.
I mean, go to Zoom and then go to view options.
What happened?
I mean, go
So
to Zoom.
you need to open the Zoom screen. Minimize this one and open the Zoom screen. Minimize the browser.
Can you repeat what's the problem?
Sir, there is an annotation option by which anyone can draw on the screen while you are presenting.
It's gone.
I'm not drawing. I will present. Okay. So the point is that we know that the free I can say that the free for a free particle, the wave function is e to the power minus ikx or plus ikx, depending upon which direction they are moving, and corresponding the energy is kh cross. But here, just think about that, we are confining that particle inside a box. And in the right hand panel, you can see there is a picture of particle in box. You can visualize the particle in box, that if you have, there's a string and you have put an ant in it, then initially it can move from right to left. Once you rinse with sugar in center and with some bitter things, otherwise then its movement is restricted within the zone where the sugar is there. So particle in box is like that. So the Schrodinger equation for the particle in box problem is expressed as minus h cross square by 2m d2 psi dx plus vx, and in this case our potential is 0 within the box. So throughout we will assume that vx is 0. then we will get the energy and corresponding wave function. The general solution for this Schrodinger equation is A sin kx and B cos kx. And usually, applying the boundary condition, we get that at psi at x equal to 0 is 0, and at L it's again 0. And applying this condition, we get the general solution psi x is equal to sin n pi L into x, and corresponding energy is n square h square 8 ml square. So and this energy is quantized, and it depends on the box length and mass of the particle. In this tutorial, we have two primary objectives. First, we will try to solve the Schrodinger equation, solve the wave function in different way. If that suppose that if our boundary changes from 0 to minus L to minus L by 2 to plus L by 2, then what happens? Whether energy changes, and if the wave function changes, how it changes. Usually, we can calculate it by two separate ways. One is go to the general solution that given in equation 1, then applying the boundary condition, we can extract the wave function. But in this case, we will opt another way by just bypassing this first process and just we want the shifting our origin from 0 to minus L by 2. In this case, in the equation that psi n equal to sin n pi x by L into x, if we replace by x plus L by 2, then we see that the wave function becomes sin n pi L x plus L by 2. Now, if we choose n equal to 1, that is the ground state, then the calculation reduces to cos pi by L into x. Similarly, when we choose n equal to 2, it reduces to sin 2 pi by L. That means, depending upon the value of n, that's a principal quantum number, n is on the principal quantum number. So, depending upon hello? Hello, Jonathan? Hello, can you hear me? Tell me. Hello, sorry, I'm there. Very sorry, I'm again starting from the second condition that we are replacing x by x plus L by 2. Then applying, then choosing n equal to 1, we reduce it to cos pi by L into x, and when we choose n equal to 2, we modify to sin 2 pi by L into x. That means, and if we further proceed, then we will see that for n equal to odd state, that means input 1, 3, 5 and all, we will get a wave function of the form of cos. And when we choose n even, the 2, 6 or 8, we will see the wave function of the form of sine. And we know that cos is an even function. So it contains even parity. Similarly, sine is an odd function and it contains odd parity. Now, the point is that when we have the boundary from 0 to L, we have a solution that is true for all the states, and we get the solution of sin n pi by L into x. When we move to minus L by 2 to L by 2, we see that the wave function, depending upon the value of L, n wave function changes, and n have the value when n is odd, we will get a cos solution, and when n is even, we will get a sine solution. Further, if we keeping the box length same, if we change again the boundary from minus L by 4 to 3L by 4, then what will happen? Again, we have the same procedure by replacing x plus L by 4. In this case, I just want to point out that we can also replace x plus 3L by 4. Then also, then sorry, x minus 3l by 4, then also we will get the same results. So here we have chosen that x should be replaced by x plus l by 2. And we see that after certain calculations, Brown's wave function is a combination of sine and cos function. Then when we move to the first excited state solution, that means n equal to 2, we see that the solution is of cos form. Similarly, again, when we move to when we choose n equal to 3, we see that the solution is again a combination of cos and sine function. So, in a broad sense, if we see and compare, if we see a general solution given in equation number 1, if we see our general solution given in equation number 1, then we can see, then it's very clear that the solution of this particle in box is a combination of sine function and cos function, and the existence of A and B modifies the function into either sine form, cos form, or their combination. So the wave function for a particle in box will always be a combination of sine and cos function. Now I just want to say you, if you have any questions, just ask. Hello?
Sir, I have a question.
Just ask, please ask, or you can type.
Sir, my question is, so when we are changing the length of the box, our wave functions are changing accordingly. Is it so?
No, look. Our box length is fixed. Initially we have chosen 0.
Yes, sir, and we are taking segments. We are taking particular segments like L by 4 to 3L by 4.
But the box length, total length, if you see, it's always L. 0 to L is L. If you shift your axis from 0 to minus L by 2, right side is L by 2, even the box length is always L.
So can we say the symmetry of the box is changing as we are changing the segment?
The boxes is changing. It's a very good point that when it's minus L by 2 to plus L by 2, then it's symmetric box. That's why we are getting a cos solution for when n is odd, and we are getting even sine solution.
And sir, if A and B are the parts of the general solution, and it changes as we are taking various segments. So, sir, A and B are the amplitude of the equation.
Yes.
So, sir, how is that changing when we are taking particular segments? So, because if we are considering a particle which is present in the segment, then, sir, how is the amplitude changing with this?
Because
Sir, sometimes it is cos function, sometimes sine.
Yes, because your boundary is changing. Look, when you take the 0 to L, then the boundary, look at the boundary condition, that at 0 the potential is infinite.
Yes, sir.
At L, potential is infinite. Similarly, when you go to minus L by 2 at the boundary, so actually you are shifting the box.
So that is how amplitude is changing according to shifting of the box.
Yes.
Yes, sir. Thank you, sir.
So that means changing the boundary will affect your amplitude.
Sir, my question is that we are changing the boundary that is according to our convenience. Means the particle doesn't know that it is x equal to 0 or x equal to L or x equal to minus L by 2 plus L by 2. That is done by us in accordance to our convenience to calculate. It will be easy to calculate the boundary conditions. But why they are affecting the amplitudes?
No, because actually particle is sensing the change because your boundary condition is changing. That means you have an infinite boundary, once in L by 2, another in L, 0, and again in minus 3 L by 4. That means the position of the boundary is different. What's length is fixed? So it's actually sensing. Look, I just point in your point. I just want to say you that when it's minus L by 2 to L by 2, it's a symmetric box. But in other cases, symmetry is lost.
My question is another thing is the particle inside the box, the same box with length L. I can change my coordinates according to my convenience. I can once set the length to be minus L by 2 to plus L by 2.
Yes,
Minus.
But instead of your coordinate, there is also a boundary condition there, which is also changing. You have to
I think it is due to the potential actually.
That's what I'm saying.
When you use minus L by 4 to 3 L by 4,
Once is potential is infinite at 0 once, and potential is infinite at minus L by 4 once. So this is the point. The potential position of the boundary is changing. That means the potential becomes infinite at different position, though your box length is fixed.
in that time we have to integrate minus L by 4 to 3 L by 4. Then according to this, the wave function will be changing.
Integration is, but physically, if you see that your particle is one particle, it's not the same when one particle is moving from minus L by 2 to L by 2 or minus L by 4 to 3 L by 4 because the position of the infinite barrier.
Yes, the boundary condition will be changing.
Yes, like you have restricted one particle from minus L by 2 to plus L by 2, another case is restricted from 0 to L, so they are all three different systems. Because if you think that this just you are shifting your coordinates, then it means that all of them have the same wave function. If that happened, but actually it's not happening because position of the boundary means you are experiencing a barrier at different points in space. Is it clear to you?
Yes, sir. Yes, sir. I think that the origin also shifts accordingly. When L by minus L by 4 to plus L by 4, the origin also shifts. So the solution, yes, sir. Yes, sir. Thank you, sir.
Actually, I just point you out that we are using the shifting of the origin concept just to bypass that calculation. That's finite bound, so that boundary condition becomes 0. So everywhere you use that convention to calculate. But if we bypass this, then this is more easier way to extract out the same result.
It means the position, absolute positions will be the same, but according to the convenient coordinate system, they will be seeming like they are changing. But absolute coordinates.
Only the box length is fixed. Their position is not changing. Sorry, their position is changing.
Yes, yes. I understood. Thank you,
Their
sir.
position is changing. Only the box length is fixed. This is the point. Okay, just go ahead. Just ask. Okay. Then now the point is that how does this system is of physical relevance? Hello? Hello? Can you
Yes,
hear
sir.
me?
Yes, sir. Yes.
Now the point is that the system we are discussing, why we call it the confined system, how it has certain physical relevance. So in this case, I can say you the most simplest model of quantum confinement is particularly box without a potential. So imagine that you are putting a gas or something in a vessel and you are applying torques of pressure onto it. Then what will happen? Its movement will be restricted within that region in the vessel and it cannot go out. And if your order of pressure increases, then it will get more and more into the vessel. So this is the premise. So high pressure physics, in high pressure physics, this model has its application. Okay. Now we move to calculate its energy. Okay. Energy expression is very simple. So we can see that the energy value is n square h square 8 ml square. Where we know that m is the principal quantum number, m is the mass of the particle, l is the Box length, and here the point you asked that previously that we are shifting the boundary, so only the origin is changing. But here is the point that in all these three calculations, we have kept Box length fixed. So if your Box length is fixed, then whatever your wherever your boundary is, whether you have put it in L by 2 or you minus L by 2 to plus L by 2 or 0 to L or whatever you like, your energy will remain always n square h square by 8 ml square. This is the virtue of this energy. And secondly, you can see that the energy value is quantized. That means you have integer value of L, and for the integer value of L, your energy exists. So I just in this point, I just want to ask you one question. Can you comment that whether n is positive or negative here? Because your n is n square, n is in the form of square. So if you choose 1 or minus 1, it will not affect your energy. What you will choose? Can you answer?
Integer.
It will be positive only.
So integral values of n.
But my question is that whether it will always be positive or always be negative or negative positive both.
So for 1D, it will always be positive because the energy is not degenerate.
Okay, but 1D is positive, energy is degenerate, fine. But just think in a different way. If you put, now I just want to find out that forget about positive integers, put minus 1. Whether energy will change.
Sir, does minus 1 even have a physical significance?
That's the point we want to come finally. That's the conclusion we want to draw. But how we could draw it, that's my point. So imagine that you have minus 1. Is it be allowed? Energy allows you to do that. Does energy allows you to do that?
Sir, minus should mean any direction or of any some kind.
No, just think about from the point of view of your energy expression.
Minus means attractive energy for minus.
Look, if you put minus 1 instead of 1, what will happen?
Nothing because it's square.
Nothing will change? Hello? Nothing will change?
Yeah, we get the same En value.
Due to the non-degeneracy criteria, now we can, from the energy, we can conclude that due to non-degeneracy criteria, we can choose either negative value or positive value. Hello? Can you hear me? So either negative value or positive value. But the point is that we have another point here that corresponding for each of the energy, we have corresponding wave function. Now the point is, if we replace n equal to 1 by n equal to minus 1, then whether our wave function remains the same or not?
No, it won't.
Sorry, non-degenerate state, we have only one wave function, or they are linearly dependent form. That means their normalization constant may change, but as a whole, wave function should remain same.
I guess the value of n comes from the quantization condition, right? The boundary conditions rather. That is what gives me.
Can you please speak louder? I cannot hear you.
Sir, I think that the value of n comes from the boundary condition itself. So that is a limitation on value of n.
Okay, boundary condition. From the boundary condition, obviously, from the initial equation, you get k equal to n pi by n is fine. But if your n and n goes to minus n, from there, that's a problem. If your n goes to minus n, then your wave function will get changed. Okay, so point is that you have only one eigenfunction for a particular state due to non-degeneracy. So if that function changes, it's not possible. That means though energy allows you to have both negative and
Excuse me, sir.
positive.
Sir, also n is the number of modes. The
Number of-
vibrational nodes, sir. How can it be negative?
N is a principal quantum number. Look, n is not in particle box. N is not the number of modes, or it's n for zero state. It's one. For ground state, it's one. So in that sense, you just think it's as a principal quantum number.
Okay. Okay, sir.
Okay. So when
Why it's one, sir? Because we from the boundary condition we get sin KL equals to 0, means K equals to n pi. N can be 0 also.
no, if you get n0, then what will be your general solution? Just go.
Will not.
Then psi will be 0.
Your
Then psi will be 0.
Equation 1, you see that if your n is 0, then psi become 1. It's a constant.
So it cannot be. Yes, sir.
K equal to n pi by L, and cos again that n pi by L, then your sin 0 is 0, cos 0 is 1, so it will become a constant. So that's why n0 is not possible. And again there is another condition that I am going to explain you soon why n is not 0. So the point is that so you have only positive value of n, and with change of L, it will only change. When at a particular n, it will only change when your L will change. Now we come to the point of 0 point energy, where we were discussing about the value of L. Why n0 is not allowed. The point is that think your energy is divided into kinetic and potential energy. Then, if in this case your potential energy is 0, because within the box, particle has 0, particle is experiencing 0 potential, has 0 potential energy value. So total energy is its kinetic energy. Now, you know Heisenberg uncertainty principle. What it says that we cannot measure the position and momentum of a particle simultaneously, precisely as well as simultaneously. That means at the same time, we cannot measure the position and momentum of the particle simultaneously. So the point is that if your n is 0, that means your total energy is 0. So you have 0 kinetic energy. If you have 0 kinetic energy, then from this delta x, delta p expression of uncertainty principle, your delta p is 0, then that means your delta x is approaching to infinity. But in particle box, what we see that our box length is L. That means your delta n value can never exceed L. So if n becomes 0, then it violates that condition. So there should have certain final value of energy so that the uncertainty principle is validated. Now, this point, this energy is the minimum, which is the minimum energy, because n equal to 1 is at lowest state, and for that state, you have energy h square, L square, and this energy is your minimum energy, and it is called the 0 point energy. Why 0 point energy? Because if you cool the system up to T equal to 0, that means absolute zero temperature, then it will also have that amount of energy. Okay. Now if you have any further questions, then I will go.
Hello.
Hello, please tell me.
Sir, I have a question that if we consider a system in which is very large, that is L is very large, then we consider that n is equal to 0 condition.
N is very large. Then your energy is very large. Why is 0?
No, sir. L length of the box is infinite.
When your box is large, then if L tends to infinity, it will approaches to free particle. The first, then when L tends to infinity, it will become free particle. So free particle has certain momentum and corresponding continuum energy, because in particle in box we have told you that it has energy quantized, but in free system its energy, in free system energy is not quantized. You will get a continuous energy state. Okay. Hello.
Yes, sir. Okay.
And in that case, if you go for uncertainty principle, then for a free particle, the probability of finding the particle everywhere is finite. Okay, that means the particle is spanned from minus infinity to plus infinity. So its delta S, the uncertainty in position in a free particle is infinite, and that's why we get a exact momentum for free particle, and that is of kh card. And this can have any real value. Okay. Now, is it clear for you? Hello.
Yes, sir.
Okay.
Hello, sir. Hello.
Hello.
So the n in this case and the n in the Bode's model are the same.
Can you repeat, please?
N in this case and n in the Bode's model are the same.
I cannot hear you. Can you repeat, please? Hello. Just louder.
Sir, n in this case and n in the Bode's model, is it same?
Bohr model, yes. This in Bohr model, we use the n as a principal quantum number, and here is again a principal quantum number, so this is same. But your system is different because Bohr model is for hydrogen atom, and in that case it's a Coulomb interaction, that means minus z by r, and here you have a potential, you have a particle within a box with no potential. That's the difference. Only the system is different, but n is same.
Sir, someone in the chat is telling it is not
The
same.
n is not same because for different system, the principal quantum number represents different things.
Look, quantum number is here indicates a quantization. Okay, but the point is that the property of that number is different here. But in a Bohr model, you see that this n is for hydrogen atom, and your energy value is minus z square by 2n square. So your energy pattern is that your energy is decreasing with increase of n, and it has negative energy. Now in this case, you have energy which is increasing with increase of n. So a system have a principal quantum number. Now in quantum system, by virtue of its existence, has principal quantum number. Then again in hydrogen atom, you get
But the quantum numbers are the properties of the system that we define. So if the system themselves are different, the quantum numbers are in principle different. We call them both the principal quantum number, but they are in nature very different. So they are different actually.
different means that look, my point of view in terms of energy is that you have allowed values of n in energies 1, 2, 3, that's its energy is your quantum number is quantized, and in Bohr your n is again 1, 2, that again the idea that came that it's again quantized. So if you are doing it in one dimension, it's a particle box. So that in that case here only one quantum number exists. In hydrogen atom there are 4 quantum numbers. Okay, and if you even in part in Bohr model you are doing it in 3 dimension. That's so. The point is that n and that n is same in that sense. The point of quantization. This n incorporates quantization in a system. Principal quantum number in both particle in box and hydrogen atom incorporates quantization. In that sense, they are same. Okay. Hello?
Yes, sir.
Hello?
Yes, sir, you are audible.
Okay, and now you have any further question or I will proceed?
Sir, sir. Hello, sir.
Tell me.
Sir, according to classical theory, sir, you are listen me.
Yeah.
Sir, according to classical theory, each and every energy level are possible. Then we said n is a fractional.
Look. In class, there is a basic difference. Look, in classical mechanics, you have any possible handling of energy. That means your energy is not quantized. But when we are in this case, you have certain allowed values of energy. Only n equal to 1, 2, 3, 4 are allowed. Integers are allowed, not all values are allowed. So in class, and wherever in classical system, any value is allowed. Any value of energy is allowed. That's the point. So this is the difference here that its energy is quantized.
Yeah.
Hello, sir. Hello.
Thank you, sir.
Sir, I have one question. Sir, if we take the length of the box as L, we'll have certain wave functions for the particle. If we halve the length of the box, what will happen to the wave function?
Yeah, if you change the length, then your wave function will have the same form, but the length will change. Only the length will change. If you change your boundary in that sin n in the first page, just go there, sin n pi by l into x. If you have box length n to 2l, if you have suppose from 0 to l, you have starting from 0 to 2l.
So substitute L by 2.
You can, because your boundary condition will change. Your first one is fine. X equal to 2l, you have 0. If you put it here, then you get a solution which will have the form of sin n pi by 2l into x. Okay. So your l will be replaced by 2l. Okay.
Sir, this actually was asked to me in an interview at JNCS.
Can we repeat?
Sir, this was actually asked to me in an interview for the JNCS, sir.
Okay. Now you have the answer now.
I answered, but I made some mistakes. The madam was asking what will happen to the wave function with respect to the bigger box. So she wanted me to use the properties of wave function and something like that. I told I was able to answer a little bit on it.
Okay, then actually she asked you to apply that boundary condition.
Yes.
This one. Just 1 second. This part. Your sin x equal to 2l equal to 0.
Okay. Thank you, sir.
Okay, now I'm moving. So next part, what we are trying to study is that we have calculated our energy by solving an equation of a particle. But is there any other way to calculate that energy of the particle in box?
Yes, sir.
Okay, tell me.
Provided we have the wave function, we can do it by applying the operator.
No.
Energy.
Just think we don't have the wave function.
Sir, we can use momentum.
Because for the ground state, delta x is total that we have, that entire L. So for that we can use the uncertainty principle and obtain delta P, and from that we can calculate.
You just speak louder because I cannot hear you.
We have for the ground state, we can have delta x equal to L. For using that and using Heisenberg's uncertainty principle, we can obtain delta P, and from that we can obtain the energy value.
No. I am telling you, no, you will not get, because I told you not to use the wave function. Okay, so in that case, you are using the uncertainty principle, then your delta x is L, it's fine. But the right hand side you have greater than equal to sign. So if you do that, then your delta P is equal to h cut by 2L, and this greater than equal to. So
I said ground state. That's why I said ground state.
And if you no, the point is that how you get your average P. Because it is greater than the P.
So
Yeah,
that
the
is
result
the dropping hypothesis.
Yeah, the result you will get, it will told you, if you use uncertainty principle, then your result will tell you that your ground state energy is greater than equal to H cross by 8 ml square. But the point is that your ground state energy is exactly equal. It's not greater than equal. So now I am answering you that there are certain ways where you can calculate the energy without employing the wave function and eigenfunction. First formula is the de Broglie formula. You all are familiar with this formula? Hello?
Yes, sir.
Okay.
Yes, sir.
Wave is equal to h by p. That h your Planck constant and p your momentum. Then your lambda for a particle in box is this your total wavelength, and this is a L by L. Here in this case I have shown you for n equal to 1 case. Then your lambda is L. But when you increase your n value, then it will change. Okay. So if you put the values, you can check that then your P becomes NH by 2L. Now just certain adjustment, you can see that we have got the kinetic energy. And we know that particle in box have only, in the box, particle have only the kinetic energy, no potential energy. So this is one way. One way to calculate, and in uncertainty principle, what you get is only the ground state energy. But here you are getting the general value of energy. That means the energy for all possible n. Okay. Now another way is that the Wilson-Sommerfeld quantization rule. This Wilson-Sommerfeld quantization rule says that area of your phase space, that P is your quantum number, P is your momentum, and Q is your space, that cyclic integral of your phase space area again is quantized. So we can replace this P by from the form of energy like that it is your root over 2m into Pn minus V, and inside the box B is 0, so it reduces to this form. And your cyclic integral of your dx is 2L. So again your energy reduces to n square h square by 8ml square. So these are the two problems. Sorry, these are the two ways by which, without knowing the wave function, we can calculate the energies of a particle in box. Okay, now again you can ask if you have any queries, please. Hello? Hello?
Yes, sir.
Sir, could you explain for the first method, lambda equals to 2L by N? So could you explain how did we get it? Like, is it something experimental, or we have assumed it empirically?
You can draw it. Look, if you say that you can see this one, that you complete your wave. This is for ground state. So you will get that when for n equal to 1, you will see this one. Now,
Yes, sir.
now just follow this. When your n is equal to 2, then what you will get like this, and then again it will come like that. So it's so the lambda, the amplitude will change. When you
Yes, sir.
can you please?
Yes, sir.
So
Amplitude,
that,
yes,
if
sir.
you have n equal to 3, then you will get like this way. I can So in this way, you can get lambda by 2l. It's a propagation of wave. No, it's going and
Yes, sir. Yes, sir.
so that's why you are getting.
Oh, thank you, sir.
So now if you have any further questions? Okay, now I'm moving to the another point that we have discussed already before, the 0 point energy. So we know that the 0 point energy is the minimum possible energy for a particle. And if you apply the uncertainty principle, it allows the existence of, and also explains the existence of the ground state energy of the particle or the 0 point energy of the particle. Now, our point is that if we have the minimum uncertainty state, that means this expression that delta x into delta px is greater than equal to h squared by 2. Now the point is that if we see that for which kind of function or for which kind of state this delta x delta px becomes equal to h squared by 2. Okay, so now we will follow this.
Excuse me, sir.
Hello? Tell me.
Excuse me, sir. Sir, a question.
Yeah.
Sir, in Heisenberg's uncertainty principle, why do we always take the pair of position and momentum? And like energy and time, why always these pairs are taken and not something else?
Okay, look. In general, we can construct an uncertainty principle between two non-commuting operators. If you have A and B, and A, B are not commuting, that means A and B don't have their simultaneous eigenfunction. That means if A and B commute, they have simultaneous eigenfunction, or you can construct it. But if A and B does not, if A and B do not commute into each other, then you will see they don't have simultaneous eigenfunction. They can have uncertain relation between them. But here that if you see your energy, and it has a potential energy, and it has a kinetic part, that is your momentum part, that is your kinetic energy. So your total energy is explained in terms of position and momentum. So that's why you know that the x and p are canonical conjugate to each other. That means if you have the information of one variable, then wave function for one variable, you can construct the function for the other. So that's why physical purpose is in terms of energy.
Hello, sir. Hello, sir. There are some background noise, sir. Please.
Is it clear now?
Yes, sir.
Okay. The point is that there is always an uncertainty relation between two non-commuting operators, but in our purpose, we use x or nothing.
Sir, you can mute him, sir. You are the host, you can mute him.
Sound is coming. Hello?
Please mute yourself. Sorry, you can mute these two people.
No, not that. Okay, it's fine now. Okay, now I'm good. Okay, if you have any, do you have any further questions? Okay, now I'm proceeding. So now our objective is to find out that state or that function which obeys the equality condition. So to do this, we need Schwarz inequality. What Schwarz inequality says? It says that the overlap between the wave function is always less than equal to the product of the overlap of themselves. That means you have a wave function. If you have a wave function of psi 1 and psi 2, then this the psi overlap of psi 1, sorry, normalization of psi 1 with itself, and then the overlap between the psi, always their product is always greater than the overlap between psi 1 psi 2 square. So if we assume psi 1 as x minus average of x into psi, and simultaneously psi 2 equal to p minus average of p psi, then this relation reduces to this form. And we know that the commutator between x is ih plus. So if you replace this, then we will reach to the expression this. So now our point is that how, again, that our objective is to get the minimum uncertainty state, that means equality condition. So if this psi 1 and psi 2 are linearly dependent, that means if you express, that means you can express psi 2 as a product of some constant into psi 1. Then they are called linearly dependent. And if this psi 1 and psi 2 are linearly dependent, then this inequality becomes equality. So depending upon that condition, we have this equation. You can write it down that your psi 1 is equal to some a into psi 2. So then your psi 1 is x minus average of x into psi, and your psi 2 is equal to p minus average of p into psi. So if you write that, then you will get this equation. So for the simplest case, now let us assume that your average x is 0 and average p is 0, because you know that average x and p are numbers. If these numbers become 0, this will not, as a whole, this will not impact this equation to change this property. It will just, the constants will be removed. And again, we are assuming that this a is an imaginary number. Then if we do certain simple mathematical manipulation and assume a equal to I alpha, and then we leads to the expression that will become a Gaussian function. Okay, that means from this calculation we can see that if psi is a Gaussian function, then it obeys the minimum uncertainty state. And we know that this psi is a ground state of harmonic oscillator. Okay, so that means, so we are now in a position to start harmonic oscillator, but we will not start today. So if you have again any questions, just ask.
So can you once again go through this last proof, that it is Gaussian? This last proof, that the minimum uncertainty is a Gaussian. Can you once again go through this proof?
You have to repeat because I have not, you are not audible. Too much noise.
Sir, can you once again go through this proof of that the answer?
Can you write? Okay,
Sir, he is saying that can you once again go through the proof of the uncertainty principle, the Gaussian part?
I will show or I will tell you.
You just tell.
The point is that you have, if you have, from the starting I am again saying that you have the expression of del x, del product of del x, del px greater than equal to h cross by 2. Now we have a very famous inequality called Schwarz inequality, and it says that if you have the overlap between themselves, that is psi 1 into psi 1, that's dot product psi 1 of psi 1, and again psi 2, and their product is always greater than the overlap integral of between psi 1 and psi 2 square.
Sir, can I say something? Okay. Sir, is it that quasi-Schwarz inequality that we have studied?
Yeah.
Okay. Just in another.
It's yes, it's partition. Now the point is that if you consider your psi 1 is of this form and psi 2 of this form, then you will lead to the expression of this. That's your delta x square. You know that delta x means that standard deviation. That means your square of square average minus average square. That means x square average minus x average square. Similarly, p square average minus p average square. So this expression will give you this, and we know that the commutator of x and p is always IH cut. That means if you replace this by IH cut, it will lead to the expression we have taken initially, this form. So now we know that we have to get the equality relation. To get the equality, psi 1 and psi 2 have to be linearly dependent. That means just multiplying a number with psi 2, we will get psi 1. Or vice versa. That means multiplying a number with psi 1, we will get psi 2. So in that case, if we have the psi 1 of this form and psi 2 of this form, then we can write this equation. Okay, and taking this condition, this inequality becomes equality. Now further, we prove that A is an imaginary number, and we choose that this is an x average and this is a p average, and they are nothing but numbers. We choose this number as 0. And applying that idea, it reduces to x psi equal to a into minus a into p psi. Now applying this condition, it leads to the function or psi of the form of e to the power minus beta x square by 2, where beta is a real number, and this function is called Gaussian function. And you can see that Gaussian function obeys the minimum uncertainty state. Further, this Gaussian function is a ground state aware function of quantum harmonic oscillator. So now, is it clear?
So,
I have a question here.
So can you repeat how can we take x equals 0 and p equals 0?
Okay, it's an assumption. If average x is 0 and average p is 0, you can see that for a real wave function, that average p is 0. That look, average x and average p are number. So you can choose both of these number as 0. If you don't select this average x is 0.
So basically we are taking x and p symmetric, right? About 0.
Yeah, x and p are 0. That means average x is 0 and average p is 0. If you do not choose average x 0 and average p not 0, then also you can calculate this and you will get a different function that you can also do. And I think this will be a good assignment for you to do that. Just keep this x not equal to 0 and p not equal to 0 and just calculate and find out the form of the function you are getting. And I can assure you that the function you will get will again obey the minimum uncertainty state, but that will have the different form. Here I have chosen the simplest case, that both x and p are 0. So this is the simplest case or a special case. And again, you have the option to choose both x and p are finite number. Either x is 0, p is finite, or p is 0, x is finite. You can have 3-4 options, and you can try with it, and you will get different functions. And they are all obey the minimum uncertainty state. So the point is that you can check. This is one case I have shown you that this is a function which obeys the minimum uncertainty state. Okay. Now tell me. Hello?
Yes, sir, it's clear now.
Hello, if you have any further questions, please ask.
It's clear, sir. For me.
Now, I have a question here. When you began that proof, you said, let us assume psi1 is x minus average x times psi, and psi2 is p minus average p times psi. Why should we assume that?
Because, okay, this is a standard form, because if you the point is that your objective is to find this expression from this towards inequality. So to find this form, you have to choose psi1 is of this form and psi2 of this. And if you choose this, then you will get this.
So this was done for the sake of mathematics, means in order to match this.
My objective is to get an answer in terms of x and b. If you do, you can do it. But the general form is that x, a minus average of a and b minus average of b. Then you can do it. You will get a form of del of a into del of b and like that. So, but here in this case, this is the objective. That's I have chosen a equal to x and b equal to p. And it's again you can do it, but I have not done all the calculations here. I have just written the final expression. If you do the calculation here, then just put your this psi1 and psi2 in that expression, then you will see that your psi1, if you put psi1 equal to x minus average x into psi here, it will reduce to delta x square. You can try it.
It is standard deviation, sir, kind of.
Yeah, thank you.
Hello?
So is it standard deviation?
Yeah,
Average.
standard deviation. Because if you write multiply, suppose you can write here now, just write multiply with psi1 with psi1 star with psi1, and assume that psi is real. Then you can see that x into x, then minus x into average of x. Then again you get minus x into x average x into x. Then again and x average x square. So once you integrate, you will get x square average minus x average square minus x average square plus x average square. So 2x average will cut out. They will cancel each other. Finally, you will get an x square average minus x average square. So same thing for p, and you will get this form. You can try it.
Thank you.
Sir,
And I am insisting to all of you, just try to do that with taking three conditions to derive the wave function for minimum uncertainty state. One is for x0 to not equal to 0, x not equal to 0, average x not equal to 0, average is 0, and average x and p both not equal to 0. There are three different and three more cases which we should explore. Then you will find different wave functions.
It will be shifted Gaussian, na?
Okay, you try now. I'm just saying, just do it. Just three different conditions that you can apply and can extract three different wave functions which again all over the minimum uncertainty states.
Sir, can you hear me?
Yeah.
Sir, I have a doubt regarding that particle in a box. Sir, in that inside the box we take b equals to 0. That is also an assumption, right, sir? Means v can be constant.
In reality, that is an assumption. Yes. In reality, there. But this is the most primitive model of quantum confinement. This is the Then again, if you go, you can put v inside the box. Then its wave function will change accordingly, and here this bx is 0, then that bx will have a certain form, and you can solve this ordinary. The procedure is same, but this is the most simplest model of quantum confinement. Secondly, this model matched with the high pressure confinement of an atom or molecule. So that's why I'm saying.
Okay, sir.
Sir, how will the energy change if the V inside the box is increased?
Then you have the energy expression will change. Obviously, now your Schrodinger equation will change. Then you have a different wave function that will not be expressed in this form. Your general solution will no longer be of this form. So that will change. Then again, you will get the results. I can give you an example. Suppose you put the hydrogen atom inside this box. Okay, then you will get a solution of hypergeometric. That means you have a sum of the series from the wave function is expressed in terms of a sum of the series. And in that case, you have two parts of the solution. One is the exponential part, one is the pre-exponential part. That means that the part that is not in that exponential part. So your pre-exponential part will be of a special form of function that is called the hypergeometric function. And then again you will have the exponential part will take care of your asymptotic part. So that's then your wave function will change. But the idea remains the same. That's the point.
So we need to switch.
Yeah?
Why quantum computing?
Yeah. Just repeat. Hello?
That was some disturbance only, sir.
Okay, fine. Okay, so I think you have it's done now. So you have any further questions? So what today? Good night. Okay, have a good day and have a good future ahead. Thank you.
Sir, how can I contact you?
Hello?
Sir, how can I contact you in future?
Okay, you can take my email ID and you can contact. My email ID is pchem.nwtik@gmail.com.
PCHEM.
Chemistry, CHEM.
Oh, physical chemistry.
Physical chemistry, PCHEM.nwtik@gmail.com.
Yes, thank you, sir.
Okay, thank you all.
Thank you, sir.
Sir, NWTIJ.
NWTIK. PCHEM.nwtik@gmail.com. Okay. Thank you.
Very nice, Neetik. Good. Okay.
Thank you.
Yeah.
जी बंद करिए।